is getting in the right place. Yes, there's only one edge. Really get another of your friends.
And then it disengages.
All right. So the first thing we need to talk about today, when in order to get to a point where we can talk about vector surface integrals, is what we mean by an oriented surface. So a surface, the idea with an oriented surface is that it's a surface that has two sides. And what that means is that, and the other, they're called oriented surfaces. We also refer to them as orientable surfaces. So the idea is we want to be able to say, on the surface, this direction is up, this direction is down. So oriented or orientable surfaces have two normal vectors at any point. And let's draw a little picture here. So what we're saying is our standard surface, at this point, we have a normal vector, an upward normal vector, and we have a downward normal vector. And this would be negative n. So we have two normal vectors at that particular point. An example of a non-orientable surface is a Mobius strip. So let me grab a picture here. Mobius strip is a surface that has one side. So if you think about drawing a line around this surface, maybe I'll do it in red. So if I start here and I go around, now I end up back here, and I go around. I haven't crossed an edge. And I get back to there. So you take a sheet of paper and you give it a half twist and connect it together. And in the past, when we've had, depending on the time, I have some activities that we can do with Mobius strips, because interesting things happen when you cut them in half. You cut them in thirds, or you connect a Mobius strip to a regular strip of paper and cut those in half. Lots of interesting things. So when you cut it in half, this dotted line becomes an edge, and then the strip of paper has two edges, and it becomes a one-sided surface. Or sorry, a two-sided surface. Right, interconnected loops, right? And an example of a solid is a Klein bottle. So this one, it's a Klein bottle. It's a one-sided three-dimensional surface, but this point where they intersect is in the fourth dimension.
Right. Right. Of course. Yeah. Logically.
Yeah. So if you trace a line around here, you end up being able to go inside the bottle and come back to the same point without crossing an edge. This is a Klein bottle. So non-orientable surfaces. So the technical definition is for an orientable surface or an oriented surface, we need to be able to define a unit normal vector that varies continuously at every point on the surface. All right, so the way we'll think about it is our surface has two sides. We need to be able to talk about an upward unit normal vector and a downward unit normal vector. So are we good here? Oriented surfaces. So for a smooth parametric surface, R of u and v, our unit normal vector we know is r sub u cross r sub v over the magnitude of that. And negative n is in the opposite direction. So those are our two uninormal vectors at a particular point. I forgot that looked more like an R. There we go. And if our surface is z equals, I'm going to write g of xy, we can write, and we've talked about this before, capital G of xyz is z minus g of xy, and that equals 0. So we have g of xyz equals a constant, and our unit normal vector, n, is del g over the magnitude of del g. And negative n is in the opposite direction. And I just want to point out, in this case, just make this connection again, del g is negative dg dx I hat minus dg dy j hat plus k hat. This is our gradient. And we call this the upward unit normal vector. Because k hat is positive. So our z component of this normal vector is pointing up. And negative del g, we just change the signs. Minus k hat is the downward unit normal vector. And that's k hat is negative, pointing down. All right, so when we talk about our surface integrals, we're going to be interested in an upward uninormal vector or a downward unit. So we have an orientation. We want to talk about the direction. That's why we need an oriented surface. All right, so there's our first idea. Second idea that we need before we talk about vector surface integrals is the flux. The flux, in general, is the volume of something that flows per unit time. All right, and I'm going to say that here's my coordinate system. We're going to let our surface be an oriented or orientable surface. So we're going to have our generic surface up here. This is our surface S. So S is an oriented surface. And what I'm interested in is a little piece of this surface. And we're going to call the area delta S. And at that, we're going to imagine this is very small. And we can define a unit normal vector at that point. So I'm going to say that's our unit normal vector, n. And then we have a field, a vector field. Do that in green. And we'll call that F. And we're going to imagine that F, just for the sake of having some kind of physical interpretation here, imagine that F is a velocity field. For a liquid. So the F gives us the velocity at a particular point. So we're interested in the volume of liquid that flows through delta S. So we're thinking about the flux of the liquid. How much of that flows through that little piece of surface? Per unit time is, I'm going to draw a little picture here of this little delta S. And I'm going to draw F as one side of this thing, like so. And we're going to make a little oblique prism. No, this is, sorry, I'm going to redraw it. This is just, I'll say zoom in. So I'm zooming in just on this piece. So we're going to draw a little prism. And F, the vector F is going to be one side of that thing. So there's vector F. And I'm going to turn this into a prism. So let me do this, like so. Let me undo that last little bit. It's a little better. And I'll make this backside dotted. There we go. So we have a little oblique prism. One edge of that oblique prism is the vector F. Just going to draw an arrow there. There's F. And here's my little unit normal vector, N. Here. Oops, undo that. Don't want a dotted line. There's N. Oops, undo that, move it over. All right. So the volume of this little piece of this little solid, the height of this thing, this height want that to be black. Black. There we go. This is f dot n. Because n is a unit normal vector. The length of this side is given by the cosine of theta is the opposite over the adjacent. And f dot n is the magnitude of f times the magnitude of n times the cosine of theta. So that height is f dot n. So the volume that flows through this, the volume of this solid, is f dot n delta s. The base, area of the base, times the height of that little oblique prism. F dot n gives us the component of f in the direction of the unit normal vector. So this is going to give us the volume of that small oblique prism. So what we're going to do now is we're going to sum this quantity over some region in the xy plane to get the total volume of liquid that flows out of that surface per unit time. So at one little point in the surface, the volume that flows out of that delta S, little piece of area per unit time, is f dot n delta S. We're going to sum this over the surface to get the total volume that flows out. So I'm going to say sum this quantity over some region, and to take the limit as delta S approaches 0. So that sum then becomes an integral. So we've made this argument in chapter 15 a bunch of times. We did it in chapter 14 quite a few times as well. So we sum that quantity, take the limit as delta S approaches 0, and this becomes the definition of our vector surface integral. And we call it the flux integral. And I'm going to put in parentheses, or vector surface integral. The double integral over our surface of f dot n ds. And we call this the flux of f across s.
Is that a little n or a capital N?
This is a little n. Because we had to, in order for that to be the volume, that had to be a unit vector. So the surface integral of a vector field is the integral of the normal component of f. F dot n gives us the normal component at a particular point, and we're summing that over the surface. So that's our vector surface integral. We're summing the normal component of f over the surface. We multiply that times the area, and we sum that over the surface. So we can visualize this as the volume of whatever f represents that's flowing, the total volume that's flowing out of the surface. All right, well this is nice, but we're in the same position we were in when we defined a double integral, when we defined various other things. How do we evaluate? All right, is everybody good so far with our idea of a vector surface integral? Sum the normal component times the area over the surface. how to evaluate. If z equals g of xy, then g of xyz, we talked about this before, equals z minus g of xy. Our unit normal vector is del g over the magnitude of del g. And ds is the square root of g sub x squared plus g sub y squared plus 1 dA. And we decided this g sub x squared plus g sub y squared plus 1 square root is, for this surface, the magnitude of del g. Del g is partial of x, I hat plus partial of y, j hat minus partial minus k hat. Because partial with respect to z is 1. Take the magnitude of that. So f dot n ds is f dot del g over magnitude of del g times del g dA. F dot n is f dot del g over magnitude of del g times ds, which is a magnitude of del g dA. And we get our flux integral, f dot n ds, is the integral, double integral over our region in the xy plane of f dot del g dA. What you need, Miss Voss?
Fix your mat with paper.
Oh, it's still in my file cabinet in the chapter 11 thing. You can grab.
No, your answer sheets that I photocopied. The
Oh.
back sides didn't get copied. Are they still in the office?
The answer sheets?
You know the problems they do their work on?
Yes. I don't know. I'll have to look. All right, so this is how we're going to evaluate this thing. We're going to write g as z minus g of xy. This is important. We need, in order to use this form to evaluate our flux integral, we have to write g of xyz as z minus g of xy. Then we can evaluate this as a double integral of f dot del g dA, where r is a region in the xy plane. Yes?
So hang on, F dot capital N would still be correct at the end of the day if you have over R, because del G is a capital N vector. It's a normal vector, right?
Right.
Okay.
But in order to come up with this definition,
No, that's
and
little n. But
right.
then when you get to the end, it can be big N again.
this del g, yes. Yes.
Okay.
All right. If our surface is given by r of u and v, then our unit normal vector is r sub u cross r sub v over the magnitude of that quantity. And ds for a parametric surface is the magnitude of r sub u cross r sub v dA. And in this case, our surface integral, our flux integral, f dot n ds becomes the integral over our region in the uv plane of f dot r sub u cross r sub v dA. And R is going to be our region now in the UV plane. So this is how we're going to evaluate our flux integral if we have a parametric surface. Questions? So all of our stuff now that we're going to talk about, one is how to evaluate these things. We'll set up and evaluate some, but then we're going to relate these flux integrals to other things. Okay. So let's evaluate a couple of these things. Questions before we go on? So I'm going to point out when we set these up a couple of different ways you might be asked these questions. So the question might just say find f dot n ds, or it might ask the flux of f through s upward. So we want our upward unit normal vector. So the question may say, find the upward flux of f through s. And what they're asking you is to find this with the upward unit normal vector. Here f is given by xi hat plus yj hat. S is 2x plus 3y plus z equals 6 in the first octant. Well, since our surface is given by some function of x and x, y, z, we have our surface integral, s f dot n ds, is going to be given by a double integral over a region of f dot del g dA, where g is our function of x, y, and z. G of x, y, z is this thing, 2x plus 3y plus z minus 6. We could leave it as equals 6. I just wrote it as minus. So del g, nice easy gradient. Del g is 2i hat plus 3j hat plus k hat. We have our upward unit normal vector. Our k hat component is positive. F dot del g, nice easy dot product. Is going to be 2x plus 3y. So that's the quantity that we're going to integrate, 2x plus 3y, over a region in the xy plane. Now we need to find our region in the first octant. Well, what is that surface? That's a plane. So we let x and y equal 0, let y and z equal 0, and we put our little points here. This is z equals 6. When the other two are 0, we get x equals 3. And we get y equals 2. And we connect those. That's our intersection of our plane in the first octant. So our region is here. So we're finding the flux of that field upward through that plane. What is the volume of that field that's flowing through that plane per unit time? Well, our region, what is that line? Y equals minus 2/3 x plus 2. So that gives us our region. So the way I set this integral up, our surface integral, f dot n ds, is the integral. X is going to go from 0 to 3. Y is going to go from 0 to minus 2/3 x plus 2. And we have our quantity, 2x plus 3y. And we're going to do a dy dx order. Easy integral to evaluate, just some polynomials, nothing crazy. And this gives me 12.
No way.
Did you say 12?
Yeah.
Check the tapes.
Oh, jeez.
It's finally
You
12.
went on last year and watched the video.
Yeah, we did.
We should have no file.
I might have to edit that one.
No.
And the answer is 27. All right, questions?
Say 12 times, you're bound to eventually be right.
All downhill.
How are you going down?
All right, let's set up another one. That's a little trickier. Here we're going to say f is xi hat plus yj hat plus zk hat. And our surface S is x squared plus y squared plus z squared equals 36 in the first octant. And we want the upward flux of F through S. All right, so here we have the double integral, or surface integral f dot n ds. Since we have x, y, and z, we don't have a parametric surface. We want to evaluate the integral of f dot del g dA. All right, so here's what we have to be careful of. Here's a mistake that's easy to make. We cannot use the method that we talked about that del G equals 2x I hat plus 2y j hat plus 2z k hat. Why can't we say that? In order to get our cancellation that we had, to use this quantity, we need g of xyz equals z minus g of xy. Here we don't have z minus g of xy. We have a z squared. So in order to simplify our surface integral to get this, we need g of xyz is z minus g of xy. So we're going to say that z equals the square root of 36 minus x squared minus y squared. And g equals z minus the square root of 36 minus x squared minus y squared. And del G is not terribly horrible gradient. X over that square root I hat plus y over that radical. And we've seen problems like this before. We know this is going to simplify relatively nicely, plus k hat. There's our upward unit normal vector, or upward normal vector. Sorry. And f dot del G? Well, here's my f, reminder what f is. So we get x squared over that radical was y squared over that radical. And these quantities and the fact that our surface was what? What kind of surface is that? It's a sphere. So what is this going to suggest in the xy plane? For our
Circle, yeah.
a circle. So what are we going to use? What kind of are we going to set up our integral? Polar. Use polar. These quantities, x squared, what x squared minus y squared. Those are nice. But we want to set up a double integral in the xy plane, and I have the z here. Z is equal to square root of x squared minus y squared.
Full circle.
Plus the square root of 36 minus x squared minus y squared. And what does this simplify to? So we get our common denominator, so we multiply everything by 36 minus x squared. Sorry, 36. So this 36 over the x squared minus the x squareds in and y squareds in the denominator cancel, and we just get this. All right, so all that work, so this becomes our integrand. In polar coordinates, that's not going to be too bad. All right, so our surface integral f dot n ds is going to be the integral. And did we say first octant, 0 to pi over 2? Integral from 0 to 6, our sphere's radius 6, 0 to 6 of 36 over 36 minus r squared, square root, RD theta. All right, what do we have to be careful of here? This 36 minus r squared is in the denominator. Where's that going to give us a problem? When r equals 6. This is an improper integral.
Oh, nice. Mr. Beaver. Wow, let's kick it back. Oh.
Yeah, we talked about going back to Calc 1, and now we're back in Calc 1. This is improper. Yes, so this is going to be the limit as b approaches 6 of the integral from 0 to pi over 2, the integral from 0 to b, and I'm going to do the first integral when we do this. We could do that. The theta integral just gives us a multiple of pi over 2. So I'm going to erase that then. Pi over 2. Integral from 0 to b of 36r over square root of 36 minus r squared dr. So that becomes the limit as b approaches 6, pi over 2, of negative square root of 36 minus, whoops, and I need a 36 out here. (36 pi over 2) limit negative 36 minus r squared. And we're evaluating that from 0 to b. And now that's in the numerator. That doesn't give us a problem anymore. The limit is fine. And we get 108 pi. All right, that one was really nice.
That was
All right, this next one I want to talk about how we would set this up. We don't necessarily have to go through the entire thing. Here we want to find the flux through the closed surface,
Oh boy, it's gonna be zero. Can it be zero?
where n is the outward normal vector. The other way you would be asked this question is f dot n ds. That circle represents a closed surface. All right, so f is x plus y I hat plus y j hat plus z k hat. And our surface is z equals 1 minus x squared minus y squared. And z equals 0. Those are the boundaries of our surface. So what is that thing? Paraboloid. And the z equals 0? That's the bottom of the paraboloid. So here's my, in the first octant, here's my surface. So to get the total outward flux, we need to evaluate two integrals. We have to find the flux out of this paraboloid, and we also have to find the flux out of the bottom. So for a closed surface, you have to consider all of the boundaries.
What if it only has one boundary? Like a sphere?
Well, a sphere, then you could just do one. But this one, we have, because of the way we defined it, it has two boundaries. If you had a cube,
You have to do 6.
a closed cube, you have 6 boundaries.
Yeah, we did this. Yeah, we did that in physics.
Three cubes down, three cubes.
All right, so we need
Except you didn't have to do integrals.
2 integrals. One for the paraboloid and one for the bottom of the surface. So let's look at the bottom first. Now, before we set this up, the fact that our surface is a paraboloid, what's that going to suggest for our coordinates? Polar coordinates, because our region in the xy plane is a circle. So look at the bottom first. What is an outward unit normal vector for the bottom of this surface? N is negative k hat. F dot n is negative z. And our surface integral for that particular surface, f dot n ds, is going to be the integral over our region of negative z dA.
Why is it just negative z at the bottom?
Just negative z.
For
That's a flat surface.
yeah, it's just that circle in the xy plane. So the outward unit normal vector is just the normal vector to the xy plane. Well, on this surface, what does z equal?
0.
Z equals 0.
Wait a minute.
There's no flux. It's just a
So the field, there's no flux through the bottom.
Hey, someone's been seeing
So that particular surface integral gives us 0. There's no flux through the bottom. On the other portion, On the other portion, we have z equals 1 minus x squared plus y squared. We need z minus g of xy. So we have g equals z plus x squared plus y squared minus 1. And del g is 2xi hat plus 2yj hat plus k hat. F dot del g, it looks kind of ugly at first, but it's not too bad. F dot del g ends up being x squared plus 2xy plus y squared plus 1. And then we're going to convert this into polar coordinates. So f dot del g is equal to, we have an x squared plus y squared, r squared, we have a 2xy, so we get 2 r squared sine theta cosine theta. Is it 2r squared? No, when we do the dot product, we just end up with 1, x squared plus y squared. And then we get a plus 1. So that's the quantity that we're going to integrate. And that turns out not too bad in polar coordinates, because you have that sine theta, cosine theta. That's going to be a nice, easy integral to evaluate. I'm just going to shortcut to the end. So we're going to go from 0 to 2 pi, 0 to 1 for my radius. My quantity is r squared plus 2r squared sine theta cosine theta plus 1 r dr d theta. Not too bad to evaluate. 3 pi over 2. All right. What the divergence theorem will do for us is simplify this surface integral over a closed surface. So we won't have to do multiples. But we'll have to do something else.
Why this whole chapter has just been, here's this big case, now here's a shortcut to avoid doing this big.
Right.
Now here's a shortcut to avoid that other shortcut.
That's not regulation there, Ben.
Oh, how do you about not being regulated?
Class quickly, Sean. So am I behind you.